Okay. So did you have any questions on chapter 4?
Not at all, no.
From your reading or that? Is that okay?
Yeah, it seems to be okay.
Yeah. Okay. And on the exercises, or?
I've not actually attempted any exercises yet.
Okay. So as I said in the reading notes, the first batch of them, up to around question 20, is mostly based on examples, testing whether this or that is a group, subgroup, and so on. And just some of the things we're going to be talking about in these exercises. So last time we met the definition of cyclic group on that. We might have specifically said, but we do have word order. Used in group theory well, it's used in two slightly different ways. So you can say the order of a group, order of group G, and it's written absolute value of G, if you like that. So that's referring to the number of elements in G. The group is finite order. Sorry, if the group has a finite number of things in it, it's a finite set, and the order is just that number, otherwise it's an infinite group. But the order of an element, we got an element G, and this is probably written as OG, or maybe even some books might use absolute value of G, although I don't think that's that common. But OG, or just simply said as the order of G, this is the smallest integer n, strictly bigger than 1, such that, greater than or equal to 1, such that G to the n is equal to the identity. So if you're in a finite group, every element is finite order, because there's only a finite number of elements there, and all the powers of G will have to be contained in the group by closure. So eventually, raising G to to increasing powers will eventually have to bring it back to the identity. But if it's an infinite group, then potentially the element could have infinite order as well. And it also this also satisfies, of course, that the order of group element is the order of the cyclic subgroup generated by that element, okay? Because that's the order of this set of elements. You've got G to the 0, which is the identity, G itself, G squared, etc., all the way up as far as G, say, to the n minus 1. But then if you go to the set G to the n, well, if n is the order, n is equal to the order of G, then G to the power n is equal to the identity. So you're just relisting that first element. And if you go on and look at G to the power n plus 1, but then G to the power n plus 1 will just be equal to G, because G to the n is the identity. Okay. So really they're the same concept, because the order of the group element now, we understand, is just the order of the subgroup generated by that element. Okay. So there weren't any particular exercises that left out of you or about? Okay. Okay, well, let's, from question 23 on are some of the more kind of group theoretic ones. So let's have a look at those. For question 23, they see here that A, B, and G. So it's first of all, just notice that it's completely general. We aren't given any information about the group G at all. So just have to consider G as being a general group. We don't know whether it's abelian or non-abelian. We don't know whether it's finite or infinite. So we have A to the G. So first of all, we want to prove that the order of A is equal to the order of A inverse. That's interesting. That an element and its inverse, they have to have the same order. Well, if the order of A is equal to n, i.e. we have A to the power n equals the identity, well, one thing, I mean, what would you do then to be able to start drawing conclusions about the inverse element of A?
So like A to the negative n equals yeah, like A to the negative n equals the inverse equals identity as well.
Yeah. So what are you doing that justifies that?
Oh, just inverse A to the n.
Yeah. Just taking the inverse. So if you have these two elements equal to each other, then their inverses must be.
Yeah.
And here you've got A to the n, here you've got the identity, and of course the inverse of the identity is just the identity. A to the an to the power, the inverse of an we write as a to the power minus n, and we understand that that is equal to the inverse element raised to the power n. So that's equal to the n. That's equal to the identity. Now, that proves that when you raise A inverse to the power n, you get the identity. That doesn't quite prove that the order of A inverse is equal to n yet, because who's to say that there isn't a smaller n such that there isn't a smaller n such that A inverse to the power n is equal to the identity. But I mean, these implications here, you see, I've written them down as one-way implications, that this implies that, implies this, implies that, but actually, could I do better than that? They are actually equivalences, okay? Each of these operations that I've done to reach this conclusion, they can be done backwards as well. So what we have there is that this observation now that, well, if you raise, if A to the power n is equal to the identity, that's equivalent to A inverse to the power n being equal to the identity. So you can't have one of the elements raised to the power n equal to the identity and one of them not. the smallest such positive number that the element raised to the power n equals the identity has to be the same in both cases. Okay? So the solutions to a to the x equal e and a inverse to the x e are exactly the same. It's exactly the same elements that make exactly the same powers that make each element equal to the identity. So the order of A has to be the same as the order of A. Yeah. That's it. Now there's ABC in this, question 23. B, we want to prove that the order of A, so he is using straight bar notation here, so order G, so we are using straight bar notation for the order of the group element. Wasn't sure if he was using that notation or not. So here we want to show that the order of an element is equal to the order of G inverse AG for any G in little g in the group. So this operation, remember, I think we brought this up before, this is called the conjugation operations. This is the conjugate of A by the element G. So we're in a general group now. See, if we knew G was abelian, then we'd know that, well, I can just simply move these factors around and G inverse G will be the identity. So really, we just have A on both sides. So obviously the order of A is equal to the order of A. But we can't assume that G is abelian. It's just going to be a general group. So G inverse AG is probably a different element than A. So but yeah, it does have this relation to it, that it has the same order. But you can kind of see what's going on, because so notice that for any integer n, what happens when you raise a to the power n? Well, that's equal to G inverse AG to the power n. Of course, when you put a load of those together, when you multiply a load of these together, everywhere in the middle you have these pairs G inverse. And then you have another A, and then G inverse, and then another A, then G inverse. So those inner pairs G inverse all cancel with the identity matrix. So you're just left with G inverse A to the power n G. So if this element here, this element is a conjugate of A by the element G, but then the same thing holds for any power of A. A to the n is the conjugate of, this element over here is the conjugate by G of A to the power n. Get this nice relation. So if A to the power n is equal to the identity, this implies that, well, that's the same as saying that G inverse AG to the power n to the identity, and that's the same as saying that G inverse A to the n times G is equal to the identity. Sorry, I'm just kind of losing sight of what I'm trying to prove that they have the same order. Great. Yeah, I think that's just. I think I was expecting it to be more of a calculation than it is. So the key thing is just
recognizing this, that if this element here is the conjugate of A by G, then this element, the conjugate of A to the power n by G, will give you sorry, no.
Sorry, I've been sorry. I shouldn't have A to the n over there. Sorry, that's not correct. So stop this. Sorry.
This is the key thing to observe. That if you raise this bracket to the power n, it's the same as the conjugate of A to the power n. Sorry, I wasn't justified in putting A to the n equals this. Because it isn't that, yeah, A is not equal to G inverse AG. Well, it might be in the case that the group G is abelian, but it won't in general. Okay, but this power of this conjugate G inverse AG is just equal to the conjugate of A to the n times G. So if this is what we if G inverse AG to the power n is equal to E, that's equivalent to saying G inverse A to the power n times G is G inverse AG to the power n. If that's equal to E, that's equivalent to saying G inverse A to the n times G is equal to E. And then what can we say that's equivalent to? Remember, we're trying to prove that this element inside the brackets here has the same order as A itself. Yeah, A to the n, because we can hit this on both sides with multiplying the left by G, multiplying the right by G inverse. That cancels those G's, and doing the same operation on the right, we have to multiply on the left by G and on the right by G inverse. So really, I've got G inverse there, but of course that's just equal to E, equal to the identity. So again, sorry about the misstep in the middle, but we get this equivalence. That the element in brackets, integer power of that is equal to the identity if and only if the same integer power of A is equal to the identity. So they behave exactly the same in relation to this idea. So this implies order of A, order of A is equal to order of G inverse AG. Some books will set the operation of conjugation by G as G inverse. This one does it as G inverse AG. It's just arbitrary choice. And what this was leading up to was part C. So part C is the quite nice result. So again, it's completely general. We're just looking at two elements of the group G. We will prove that the order of AB is equal to the order of BA. So we can't assume the group is abelian. So we have to allow for the fact that A times B is probably a different element to B times A. But they're not completely unrelated elements. They do, share a lot of features, and one of the features they share, supposedly, if we can prove this, is that their order is the same. You should compare this result. You kind of think about it in terms of, if you think back to matrices and matrix multiplication, so you're well used to, like, you always have to remember that matrix multiplication is not commutative. When you multiply square matrices, you can't assume that it's A matrix A times B is the same as B times A. But that's not to say that they're completely unrelated matrices. For instance, they will have the same determinant. Yeah. Do they have the same eigenvalues? They might even have the same eigenvalues. I'm not sure. I'll have to sit down and check that. But similar kind of feeling in groups here. So while A times B, we should never assume is equal to B times A unless we know the group's abelian, but there will be some connections between them. So they must have the same order. So can we prove this? Can we prove this using, and when you have these multi-part questions, the implication is that we're using previous parts. So we just proved this thing that if you conjugate any element, A, you get another element that has the same order as A. So is there a way to apply that to A, B, and BA?
Times both left sides by B inverse.
Well, when you start off with AB, yeah, so you multiply it on the left by the inverse, and multiply it on the right by
B inverse.
yeah. But that's equal to, that simplifies to B inverse A. And then we could say the order of AB equal to the order of B inverse A.
Yeah.
This order, which from part A we know to be equal to the order of B. Sorry, that's from part B. But now we know it to be the order of B inverse times A. It's quite get it for us. But you see, if we use part A, using part A, I'm not quite sure where to take this. Using part A, we would get that the order of AB should be equal to the order of the inverse of AB. And that's equal to, well, the inverse of AB is B inverse A inverse. Sorry, see that. See, these kind of things, you can quite often get them that, the feeling that, well, they wouldn't have asked us to prove A and B unless that in some combination they get us to prove C. So here's the thing on the left, the order of AB, and we want to get to the order of BA. So by applying part A, inversing it, we can get to the order of B inverse A inverse. That's kind of nice. That's B and A in the opposite order, but it's their inverses now. There's no point applying part A again. That will only flip us back to where we started. But maybe we can start trying to conjugate this. So we can conjugate by B. And then we'd end up with a B inverse here. But of course that reduces to, yes, we conjugate using, well actually we're, strictly speaking, we're conjugating using B inverse here. I'm putting, because to conjugate we put the inverse element on the left. So I'm conjugating by the inverse of B. So I put the inverse of B, namely B on the left, B inverse on the right. That will simplify, the B and the B inverse will cancel. Simplify to A inverse B inverse. Now I've got something new here. I've gotten to, I was at the order of B inverse A inverse. I've now managed to reverse that. I've reversed B inverse A inverse to A inverse B inverse. So in effect, that's the result really, because B inverse A inverse could be, I could use B and A in their place maybe. But
So this is by conjugate. So this was by part A. This is by part B. It simplifies to this, but then I can apply part A again. So the order of this element must be equal to the order of its inverse by part A. But then the inverse of A inverse B inverse is the product of the inverses in the opposite order, so that's equal to BA. So we got there in the end.
That mightn't be the fastest way to do it. It might be a faster way to do it. Well, I've done it there with 2 applications of the inverse rule and 1 application of the conjugate rule. I think you can maybe do it with 2 applications of. Might be able to do it with 2 applications of the conjugate and 1 application of the inverse. You go inverse B. Yeah, sorry, that's
Actually much quicker. Much quicker to say that the order of AB, let's conjugate it by, yeah, so that's by part B. Conjugating using the conjugating by A. Of course, the A's cancel, so that's just equal to the order of the A. Yeah, that's a lot quicker. Okay. Quite often we can find this that we go. So this version is kind of going around the houses a bit unnecessary, but it gave us a bit of a feel for it, and we noticed that we're making the wrong choice at the start. Okay, but that's a nice result to have. So like even in a non-abelian group, where AB is not the same as BA, there are nevertheless some connections between the elements that they aren't completely unrelated elements. Okay, so let's look at some of the other questions. Now, some of these refer to properties of ZP, Zn, the additive group. And so recall Zn is the additive group of integers modulo n. And think of Zn as having the elements 0, 1, 2, as far as n minus 1. Got n elements. That's the additive one. Un refers to the multiplicative one, where you're just considering the elements that are co-prime to n. Now, there's a couple of results about Zn in the chapter 4. So Zn is there's a corollary here which tells you about the generators of Zn. So Zn will always be cyclic because it's always generated by 1, and it tells you, well, actually, there are, you can identify all the elements of Zn that will be generators, because anything co-prime to n will be a generator under addition of the group. So the question I was looking at then was the ones after 23. Question 24. So let P and Q be distinct primes. How many generators does ZP have? ZPQ. You're considering the integers under addition modulo P times Q. And the question tells us that P and Q are distinct primes. And we have that corollary that something is a generator of Zn if and only if it's co-prime to n. So this is equal to the number of number of R in the range 0 less than or equal to R strictly less than P times Q, such that the greatest common divisor of R and PQ is 1. Identify corollary number of it. So we can refer to it. Corollary 4.14. So we're basically asking ourselves how many integers less than PQ are co-prime to PQ. Okay. So we're asking how many integers less than PQ. Now you see, how can something fail to be co-prime to PQ? Only if it shares a non-trivial factor with PQ. But because P and Q are distinct primes, the only factors that PQ has are 1, itself PQ, and then P and Q. Yeah? So we just have to look at everything between 0 and PQ that is not a multiple of P or a multiple of Q. However, with the benefit of the number theory course we did last year, can you remember how we expressed this number? The number of things less than something that are co-prime to it. But that was a function. This was the Euler-Toshin function. The Euler-Toshin function. The Euler-Toshin function 5. Now, the discussion in this book, I think he ends up proving, you might develop some of the theory around the Euler-Toshin function again in the book, but we developed it all last year. And in particular, we had a nice formula. If we knew the prime factorization of the argument, it was a nice multiplicative formula that told you what the value of it was. You recall, I would be, well, in the simple case where you just had a product of 2 distinct primes, this value would be P minus 1 times Q minus 1. Yeah. Remember, the general formula was that if n had a prime factorization and product of primes raised to some various powers, then the value of the Euler-Toshin function was a similar product over all the prime powers, and yet to reduce the prime power by 1 in each case. And then you also got an extra factor, which was 1 less than 1 less than. We had a nice induction proof establishing this theorem based on the fact that every integer factor is unique to each prime. So yeah, so ZPQ has exactly P minus 1 times Q minus 1 generated. Let's just look at a simple example, e.g. Z15. Well, Z15 is equal to Z 3 times 5, so this should have 2 times 4 should have 8 generators. Okay. And they will be all of the numbers less than 15 that are co-prime to 15. You should be able to identify them here. 1 will be, so we're ruling out every multiple of 3 and 5. We'll have 2, 4, not 3, not 5, not 6, we will have 7, we will have 8, not 9, we will have 10, we will have 11, not 12, and we will have 13. About 8, 1, 2, 3, 4, 5, 6, 7, 8, yeah, 8 generators. You can test that out if you take any of those and start looking at all the integer multiples of it, modulo 15. And if you take any one of those underlined ones, they will generate. 26 is an interesting one, another consequence of this. 26, so if P is a prime number, then P has no non-trivial proper subgroups. non-trivial subgroups, and P is prime. I.e., apart from, so no subgroups apart from the subgroups that we know are always around, which are trivial subgroup consisting of just the identity elements of, right, the identity element is 0 here, but the additive group of integers, modulo P, and ZP itself. Okay. This is the group containing the identity, the subgroup containing the identity, and the whole group itself. So apart from that, it has no non-trivial subgroups. So, I mean, how can we prove this using what's developed in chapter 4? Well, you have to look at the results in chapter 4 and think about exactly, you know, which ones might be relevant. Now, the whole thing is about cyclic groups. So we note that ZP is cyclic. Okay, all the ZNs are cyclic. It's at least generated by 1. Theorem 4.10. Theorem 4.10 tells you, I mean, there are a few different ways to kind of put things together to get the result. Theorem 4.10 tells us every subgroup of ZP is cyclic as well, because every subgroup of a cyclic group is cyclic, as we proved on G today. Okay, but if we let little z be an element of ZP, but you see, we can assume that 0 is less than or equal to z and it's less than p. So little z is one of the 0 up to p minus 1. Well, if z is non-zero, because we've already dealt with the fact that the subgroup consisting of just the identity element. Yeah. But if z is non-zero, then the GCD of z and p will be 1, of course, because p is a prime number. So by that other corollary then, which is 4.14, z generates all of zp. Subgroup generated by z just is equal to all of zp. So every cyclic, we already said that from theorem 4.10, every subgroup of zp is a cyclic subgroup. But then when you look at the structure of the cyclic subgroups, you find they all equal zp. So if every subgroup has to be cyclic, but all the cyclic subgroups are in fact all of zp, it means there's no subgroups apart from these two obvious ones, which are so no other meaning apart from these two, no other subgroups. So you get the idea. We're looking at these extra problems, extra concepts, and thinking about how we put together the results from the course to prove the results in each case. There's lots here. I'm just trying to see, do any of the questions leap out at you as particularly interesting, or choose a few more? That's a good question 30. Again, it's kind of quite a general setup. Just got two group elements, A and B. We assume that the order of A is equal to n, the order of B is equal to n, and these aren't just any old numbers. We're told that these are co-prime numbers. Okay? So we got a group and we got two elements which have co-prime orders to one another, co-prime to one another. Then the conclusion we're asked to prove is that if you look at the intersection of the cyclic subgroups generated by these two elements, that it has a trivial intersection. That it's only equal to the identity. We will prove the intersection between their cyclic subgroups is just consists of the identity elements. Well, how can we get to this? First of all, cyclic subgroup generated by A, the size of that is M. Cyclic subgroup generated by B, the size of that is N. Okay, it's just the definition of the order of an element. And note that H, if you let H be the intersection between the two subgroups, this is a subgroup. Is a subgroup of both subgroups. Okay, that was something back in the previous chapter. That was an example of a general result, which was that if you've got any two subgroups, their intersection is again a subgroup. That was question 45, page 49, chapter 3. So it's true in general. Whenever you take two subgroups of a group and look at their intersection, that is again a subgroup. And by definition, the intersection is a subset of both of these, so it is a subgroup. But then you look at the results in chapter 4 about subgroups of cyclic groups. So what might be relevant here? Well, we got proposition 412 and theorem 413. But well, certainly H will be cyclic. H is cyclic because that's an example of theorem 4.10. Every subgroup of a cyclic group is self-cyclic. So H is a subgroup of a cyclic subgroup. It's a subgroup of two cyclic subgroups, A and B. So it certainly is cyclic. So it's by theorem 4.10.
I'm just struggling here to find this.
I mean, I can see why this must be true by appealing to something called Lagrange's theorem, which we're going to be proving in a couple of weeks, which says that the order of any subgroup must divide the order of the containing group. And so that tells us that the order of H must divide the order of A and must also divide the order of B. That means there must be a common divisor of the orders, but the orders are M and N, the orders are co-prime, so they have no common divisors except one. That tells you that the order of H is just one. However, I don't want to use that because we haven't proved that yet. And obviously by implication we should be able to prove this just based on what we've got here. Yeah, I think we can do it with theorem 4.13. Theorem 4.13, let's just have a read of that. It says, let G be a cyclic group of order n. Okay, so it's referring to cyclic groups. Now, the G we're dealing with here isn't, we're not told it's cyclic. But the two cyclic groups we're looking at are cyclic subgroup generated by A and cyclic subgroup generated by B. So we've got these two cyclic groups. So theorem 4.13 can apply to both of them. And then it says, it talks about, well, if you've got a generator of those groups, which is called A in the statement of theorem 4.13, then if you have B, an element B is. The order of B, it tells you, is n over D. So it's a divisor of n, and the order is n over D. That's the divisor we're talking about, where D is the greatest common divisor between K and N.